Hey, Alex again. Welcome to part 5 of 5 of the ramp series. Now, despite the finality that 5 of 5 would suggest, there is going to be one more video after this to do kind of a wrap up and a where do we go from here sort of thing. And let me offer a quick apology. I was trying out a new LED lighting rig and I did not realize I have a nasty hum and buzz in some of those sections. I'll do my best to filter it out, but you're just going to have to suffer through it with me. Again, apologies. But for this one, I wanted to hit on one of the more important aspects of the ramps or any 3D printer, and that's your stepper drivers. Specifically, drivers that fall in the StepStick format. With developments recently from companies like Trinamic, Panicate, and a few others, there are a broader range of options than there were just a few years ago. And with more options comes more complexity and more variables, and I realized that I'd probably have to break that down in a little more detail. In a little while, I'm going to be making another video where I kind of drag race all of these steppers against each other and compare noise, torque, heat, ease of configuration, all that kind of stuff. So if you're interested in seeing that, make sure to subscribe and ring the notification bell, because I'm just waiting for them to show up in the mail and then I have to get my test jig finished up. So it should be soon. Trademark. This will be broken up in outline form. I'll have information chunks with a time index down in the description, because I watch a lot of YouTube videos and I know it's really annoying when someone gives a big long technical video and then doesn't put time indexes down. So for you, nothing but the best. So here's how it's basically going to shake out. First section is going to be on the Allegro A4000 series, plus a little bit of history on how the StepStick evolved. Then I'm going to talk about the Texas Instrument DRV8825 drivers that are so popular, their construction, and compare those to the Allegro drivers. The third section is going to be Trinamic in their various forms. Then I'm going to hit on Other, which is other stepper driver boards that fit into the StepStick format. And then finally, Alternatives, as in alternatives to the StepStick format. So first, a bit of history. So a long time ago, way back in 2010, Leslie Nielsen died and the whole world mourned. But that's not the point. In a galaxy far, far away called Nevada, a company called Pololu Robotics, that's Pololu, made great strides toward an onboard modular stepper driver format. Now, these were based on the Allegro A49000 series, and although they look a little bit clunky by today's standard with the onboard capacitor and regulator, but it was a huge jump up from the bulky L200 series that had been used previous to that in version 1.0, which consequently I still have on a shelf behind me. The second iteration that used Allegro A3000 series, which I think was officially numbered 2.0, that version which shall not be named 2.2 and 2.3, which eventually evolved into the StepStick format that we all know and tolerate. And that brings us up to present day. Now, these boards are cheap, they're rugged because they have thermal shutdown protection, and they're super easy to use. But they also have a serious overheating problem. You see, this chip that they used was a QFN package, which means quad flat, no leads. So on a chip like a T-SOP, you would have your package and then the leads off to the side like this. And that leaves the entire bottom that could be hooked up to a ground plane that can act as a heat sink. And then you would just extend it beyond on the PC board, and you wouldn't have any problems running into the legs, and it would dissipate your heat. But with a QFN package, they have a small patch in the middle that's usually connected to ground, and then the leads are all around the perimeter of the little 4x4 square. And since that's the case, there's no way that you can make a top etch pattern that would not interfere with the legs. This means that you're completely dependent on what's called in-pad vias, or just thermal vias. And these are basically just copper-plated holes that transfer the heat from the bottom of the chip to a different PC board layer. In our case, the bottom, because that's the largest surface area. Unfortunately, with these chips and this board design, it's just not quite enough. Now, it helps to mount a heatsink on the top of the chip, but the plastic's thermal efficiency is pretty low. And while using a larger heatsink can help a bit, it helps even more if you can get one on the bottom of the chip. Now, unfortunately, you just don't have enough room for that above the jumpers. So one thing I've done in the past is to use these extenders, and you just trim the legs to whatever length you need to get enough space that you can fit a heatsink and get a little airflow underneath, and that'll greatly improve your cooling. And I always have a PC cooling fan or a blower. And because of the way the step sticks are lined up on the ramps board, it makes a nice little conduit for blowing air across all of the stepper drivers. And electrically, you have to take into consideration what's generating the heat to begin with. These are driver chips that are pouring a lot of current into a motor. And they all have internal MOSFET H bridges with high and low sets of MOSFETs. And if you watch my MOSFET video, you can see all of the nerdy math that's involved. I won't bore you with it again, don't worry. But it boils down to just Ohm's law. The higher resistance at a set current, the more heat you're going to generate. So MOSFETs have a parameter called RDS on, which is resistance from the drain to source in the on state. The lower that value, the less heat you're generating and the less heat you have to dissipate. So our Allegro A4988 chips have an RDS on between 320 and 430 milliohms. Now that doesn't make a whole lot of sense out of context, but we'll come back to that number later when we're comparing it to other drivers. Now, even though we have a fairly small board space, 15 by 20 millimeters, it's not always the size of the package that's a problem. Sometimes it is how you use it. In terms of the board construction, you have two factors you have to think about. One is the thickness of the copper traces, and two is the number of layers of copper you have embedded in the board. Cheaper drivers are just going to have a top and a bottom, and they will have thinner copper, whereas the high current boards are going to use a 4-layer design that's going to give them a lot more heat sinking capacity. Also, typical PC board trace thickness is measured in ounces, as in ounces of copper pour, which equates to mils or microns or whichever measurement your board manufacturer prefers. But for our purposes, it'll usually be 1 ounce or 2 ounce copper, sometimes 0.5 ounce copper. And for these boards, especially the budget ones, you'll usually see 2-layer, just top and bottom, 1 ounce copper. Occasionally, it'll be 2 ounces on the bottom where the thermal vias are transferring most of that heat. And then with certain boards, you're going to see layers embedded between the top and the bottom, and that's going to improve your overall performance. So let's take a look at one of those boards now. So these are the DRV8825 driver carrier boards, sometimes also called just high current Pololus or high current step sticks. Here's a chart from reprap.org that is a basic comparison of the Allegro chip on the left and a Textron Instrument DRV8825 on the right. As you can see, the Textron Instrument chip can handle more current naturally. It also has a higher number of microsteps. They also note that the carrier card does have 4 PCB layers. And the chip does use a TSOP packaging instead of the QFN, so you can use the top layer of the board as a heatsink, although unfortunately, because of the orientation of the chip on the step stick, that nullifies that advantage, so... Another note is that the Texas Instrument drivers will take a higher voltage input than the Allegro drivers will, and that makes them more popular with the CNC guys who are trying to milk as much torque as possible out of their steppers. Now, before I go on, I should also note that there is a Pololo Black edition with the Allegro drivers on them, and they use a 4-layer board and thicker copper. I do have some of those, and I will be testing those in the torque comparison video, so stay tuned for that. A while back on the Think 3D Print 3D, aka the Duet Guys, blog, they posted some test data for 1 ounce 2-layer all the way down to 2 ounce 4-layer and found a significant difference. And since I love you all so much, I'm going to go ahead and destroy one of each of these so I can show you what it looks like inside. First, we're going to look at the Allegro chip. Grabbing this obnoxiously bright LED light, we can kind of see through the chip that it's just a 2-layer board. And in contrast, here's the Texas Instruments driver, and you can see how much more solid that board is. Now, the Allegro step stick that I took apart was particularly crappy, and it did have noticeably thicker copper on the bottom than on the top, but I'm hesitant to say it was 2 ounce on the bottom and 1 ounce on the top. It may very well have been ½ ounce on the top and 1 ounce on the bottom. After about 15 minutes of cutting, sanding, and scraping, here's the results. As I bring the flashlight toward it and away from it, you can see with the Allegro chip, you can see right through the PC board. Now, when we look at the Texas Instrument board, when I bring the light down, the internal traces magically appear. Now, you might be thinking now, well, that sounds great. Sign me up for some DRV8825s. Well, hold on a second there, because there are a couple well-known issues with these drivers that are well documented around the internet, so I won't reiterate everything, but they're prone to missing microsteps. And you can solve that problem by either using anti-parallel diodes in line with your stepper motor, or use the pre-made boards that have become known as TL smoothers. Or you can change the decay mode of the chip. Now, the decay mode is naturally set in mixed decay, but you can hard set it fast or slow if you wish. I haven't really found that solution to be better than diodes, and I am actually running two DRV8825s on the printer that's to my left right now. And while the higher voltage handling is nice if you want to make use of that, be honest, you're probably never going to be running these at 42 volts. And furthermore, even though you have twice the microstepping as you do with the Pololo boards, we actually only need 10 to 12 times microstepping to smooth out our mechanical resonance issues, and anything above that is just icing on the cake, and it makes things run quieter. But the hardware that we're using is not particularly fast, and we can only spit out about 16,000 pulses a second, and 1,000 of that is reserved for your computations. Now, another more obscure and maybe esoteric problem that we run into is that you need a particular set amount of time to get those steps to the stepper driver and then let it do its thing. If you have, for example, a tee-off time that's way too low, your stepper driver may not be able to develop sufficient current at that particular microstep. You also have a particular duration of pulse that you need to feed it in order for it to respond to the commands. These are all set by either the construction of the chip itself, the components that are on the board, i.e. the external components that are selected by the developers, and then also by user settings or the default settings. This is another reason that the DRV8825s have a problem with missed microsteps, and why setting them to a faster decay time is going to fix that, or adding the smoother diodes. But regardless, some of these drivers are going to be set up default as a rather large tee-off time or blank time, so you're pretty much relegated to the speed of that, which may be in the order of kilohertz, as in like dozens of kilohertz and not hundreds of kilohertz. So if you take your maximum step rate because of your round trip time on your driver, you divide that by the steps per millimeter, you're going to get your max speed. Now, if we're in the 20 to 30 kilohertz range, then our max speed is going to be in the couple hundreds millimeter per second range. Meaning that if we try to go any faster than that, you're just going to have your stepper driver freaking out and your stepper motor is going to act erratically. Naturally, that's going to be exacerbated by higher native step resolutions, microstep resolutions, and by using higher resolution motors, i.e. 0.9 degree motors. So the bottom line is, if you're running a higher microstepping resolution, you're limiting your top speed and you may be choking your processor, particularly if you're using a Core XY machine or a Delta. Now, Trinamic drivers have been the new hotness for a couple years now, and rightfully so. They have a lot of interesting features, and one of the more popular has been Stealth Chop, which changes the drive mode from more of a voltage drive to more of a current drive, and it allows you to run your chips with a few caveats at a much lower noise level. They'll also do traditional drive, which nobody really uses, and they have spread cycle, which is a bit more advanced type of voltage drive. If you're interested in seeing how these modes compare, make sure to check out my Trinamic torque videos and stay tuned for my future torque testing. Now, a German company called Vaterrad designed these chips into the standard StepStick format so that they will just plug into your ramps board or anything else that'll take a StepStick. And the chips that they made available were the TMC 2100, the TMC 2130, both of those obviously in the 21XX series. And then there is the 22 series they made available as the 2208. The 2100 step sticks are just regular old dumb, so to speak, step sticks that plug right in as a replacement for your Pololo drivers. The 2130s are also available with some more advanced features like stall guard and software end stops. And then the TMC 2208s are configurable over UART serial connection, and they feature Stealth Chop 2, which is a slightly improved algorithm from the 2100 series. They can also pump out a bit more current than the 2100 series chips, but the downside is you're going to need more wires. And unlike the TMC 2130s, you will have to run standard end stops because they don't have that feature either. These Trinamic chips also have software-generated microstep table. So this is not native microstepping, this is a multiplier. And the benefit of that is that you don't have to be spitting out a particularly high pulse rate to get nice, smooth, quiet operation regardless of your mode. For example, if you dig through the videos on my channel, you can find a high-speed print of a tree frog, and I use quarter stepping plus software interpolation to make it a little quieter and smoother. If I had not had the interpolation on, I likely would have run into resonance problems, and if I had run at extremely high microstepping, I would have run out of juice on my processor. So if you're trying to milk some goodness out of your Delta or Core XY printer and you keep running out of horsepower, that might be an option that you want to consider. Other possibilities are also running higher resolution steppers or running gear reduction ratios on your kinematics platform. Now, one of the improvements that Vatrot made when designing these StepSticks was they essentially built them upside down. They put the driver on the bottom so that the thermal vias would transfer the heat to the top ground plane. Then you could put a heatsink on the top, and it was a little bit easier to get airflow through there. But they did use a 2-layer board design, which is not optimal for the size that we have, and many people have used them with great success. Now, let me note here that it's all not romping through flowers with kittens and puppies with these chips. I have all the varieties of silent StepSticks from Trinamic, and I have installed and used them all for extended periods of time in various modes with various configurations. So I have a great deal of experience when it comes to debugging these things and getting them running right. And that leads to one of the first problems, that you're going to be spoiled by choice. There's a lot of options with these, and they're limited down on these StepSticks by making some choices for you, but you can go into them and change whatever settings you need. That means you have lots of opportunities to screw things up. Don't be afraid of that though, because you're not going to ruin the chips unless you burn those options permanently, so don't do that. But if you're just changing things on the fly with G-code or through jumpers or whatever, feel free to try out the options and see what works for you. The next big problem is that they are 2-layer boards, and they do have pretty high RDS on, especially for the 2100 series. The 2200 series is a lot better, and then the 2600 series, which are not available in StepSticks just because of size and some other concerns, those are even better. But these run hot. So you're going to be on this razor's edge between not having enough current to deliver torque to the steppers that you need, and pushing so much current that you're going to start missing steps because of heat. Now, you can do the set them up on risers, and they do have diode protection boards that you can use and act as risers, and put a heatsink on the bottom and the top with forced airflow. But you can spec motors, if you're doing it from scratch, that don't require as much current to get the torque that you need. Another issue is that these require a particular amount of headroom in terms of voltage for them to work. So if you're pulling like a pair of particularly crappy steppers out of some printer that you salvaged and you're trying to put it into some new machine, or just upgrade the stepper drivers to Trinamics in there, it might not work out that great if you have high voltage drop across that stepper motor, particularly if you're running at 12 volt. Trinamic didn't design these chips specifically for 3D printers. These stepper drivers are general stepper drivers for CNC motors and that type of thing, and they usually run at much higher voltages. So that low-end headroom wasn't really a consideration when designing these. That being said, decent steppers and raising your operating voltage to say 19 or 24 volts will go a long way toward fixing that. It'll also help one of the conditions that can cause your stepper motors to whine when you're in spread cycle mode, because they have to be within a particular current range as well. Crank them too high and you're going to have issues and noise. Crank them too low and you're going to have issues and noise. Now, the 2100s in particular seem to be susceptible to the heat problem, and they really don't like current over 1 amp RMS. This is true to the point that Trinamic themselves went back and amended their silent StepStick page, where they used to show that you could pump a max of 1.2 amps out. Now they say 0.96 amps out, because you really should keep it under 1 amp. So that's something you might want to keep in mind. Now, Stealth Chop is nice, and it's one of the big selling features of these boards, but you don't always want to run in Stealth Chop because the torque tends to drop off fairly steeply at higher RPMs. So if you need to be printing at those speeds, you're going to have to switch into spread cycle at one point in time, which brings us to hybrid mode. And you can set that hybrid breakpoint in your firmware, where it'll switch between stealth and spread to give you the benefits both. Technically though, if you look at the Trinamic's datasheet, when you switch modes, the printer has to kind of do a little song and dance to get it performing optimally. And obviously we don't do that when we're printing. That's not to say that it doesn't work, because it does, but people have been able to create G-code specifically to make that hybrid switchover freak out and present that as a bug. But unfortunately, I don't think that it's something that's going to be fixed in this generation of drivers. Also, speaking to the TMC 2130s, they use an SPI connection, which is nice because you can change settings on the fly and make adjustments, but the makers of peripherals for 3D printer boards, particularly the ramps, didn't consider that you would want to chain more devices off of the SPI. So there's no way to patch into that without either soldering jumpers right to the headers of your LCD display board, or running a line right from the Arduino's programmer point on the bottom out to the side and using that to feed just your Trinamic drivers. Fortunately, with the 2130s, you only need that one wire that you can daisy chain across to all of your drivers. But I have also found that those wires are particularly susceptible to noise and being jostled around. And by noise, I mean electromagnetic interference or radiation. And just having those near particular parts of my printer board, the pulse wave modulation signals tend to freak out the drivers occasionally. I did a bunch of testing on my board and found one particular place, if I stuffed the wires down and put a ferrite on them, that I didn't have any problems. But if I moved them elsewhere on the board, one of my axes or two of my axes would just freak out. Now that brings us to the 2208s that use the UART serial connection as opposed to the SPI. You have to run a Y splitter cable, and you'll have to make that yourself. I haven't seen anybody that manufactures those that you could just buy. If anyone's seen them, let me know, because I'm tired of making these things. And you need one of those for each of your drivers, and it's also going to occupy 2 spare aux pins. So if you are one of those guys that has all the bells and whistles plugged into your board, full graphics display, SD, Bluetooth, Ethernet, servos, you're going to start running out of pins real fast. So that may or may not be an issue for you. So since these Trinamic chips are more expensive than the others, I usually recommend people that they buy one that's already soldered up and give it a try, or buy one for their X and one for their Y axis and give it a try. They're fairly simple. They're not expensive to put in. You just need to make some jumpers and tweaks in the firmware, and then you can mess around with it and see if it'll work for you in your setup with your operating point with your drivers. And optimal for that would be higher operating range, i.e. 24 volts or so. You could probably get away with 18 or 19 if you wanted to use a laptop or LCD display supply to power them, along with low resistance steppers that have lowish inductance and a nice clean board wiring layout. And the final thought here is that there are some clones of these boards. Particularly the Chinese clones are egregious in that since there are a bunch of options, they used different options on these boards than on the Vaterot boards. So a lot of people are buying the cheapy clones and then going on to service forums and saying, these aren't working, help, my SPI wire isn't working, because the clones are in standalone mode with different jumper options. And it causes a lot of confusion. Just say up front that your steppers are clones when you're asking for help, and for everyone involved, it'll make their lives a lot easier. The clones also use even thinner PC boards, and they tend to use a solder mask that goes over top of the place that you're supposed to put your heatsink, which kind of insulates it thermally a little bit. You might have to scrape that away to get better thermal performance, but overall, they're going to be able to dissipate even less heat than the genuine Vaterot boards, so be aware of that. You might not even be able to hit 1 amp RMS before you get them skipping. If high native microstepping resolution is your thing, then the Panikit SD6128 might be right up your alley. You may have guessed, these use a THB6128 chip with 128 times native microstepping, and one of the interesting features of them is that it uses a particularly large die, and they're inverted so that you can place a heatsink on the top, and that's where the optimal position is. But also note, you have to run these with a heatsink or they will die a horrible death. I should note that I don't have any direct experience with these, but they are fairly popular, so you can poke around the forums if you're interested. And they have much easier access to the decay settings with just a little jumper pad. Another native 128 times microstepping chip is the LV8729. These are a lower current chip, so be careful there. But if you were looking for a cheaper alternative to the previous chips, these might be right up your alley. Here are a couple fairly new options. I ordered one of each from Pololu and I'll be testing them out, but just to give you a sneak peek, this is the MP6500. It's a 16 times stepping board that has external current control, and it uses a 2-ounce 4-layer board, so I'll be interested to see how it behaves. And this blue fella is a DRV8880, which has a whole lot of trims and fixins, and I can't wait to get it plugged into a board and try it out. I'm not positive if I'll have to do any firmware hacks to get this thing working, but it has some interesting things like digital input so that you can scale the current dynamically. It has 10, count them, 10 different decay modes, as well as high voltage handling. That brings us to the SD5984s, which are based on the Allegro A5984 chips. Now, these you can kind of think of as a cross between the Allegro and the Texas Instrument drivers. They use the TSOP package, which is oriented in a little bit more of a sane position. They also flip the board upside down like Trinamic, so you can get a heatsink on top, which is good. They feature 32 times native micro-stepping, just like the Texas Instrument chips. And they should be drop-in compatible for the regular Allegro drivers. These are available from Panikit. Also sticking with Panikit is their take on the Trinamic 2200 series. This is the SD2224, which on paper looks just like the Trinamic TMC 2208 silent step sticks, but again, I have not tried these, so buyer beware. Now, I say here be dragons because most of the support for the ramps boards are going to be StepStick format stuff, but that doesn't mean you're necessarily relegated to onboard chips. So this section is going to encompass all of the others. I won't go into too great a depth since this is less of a popular area, but a good place for you to start would be light CNC mills, because although they occasionally use ramps or like a Gerbil shield on an Arduino Uno, they will use external steppers occasionally if they want to take their current electronics and just move it up to a heavier duty machine. So they will often use external block steppers, which are much more expensive than the StepSticks, but they're much more capable in terms of current and voltage handling. We already know that the higher the voltage, the higher the torque we're going to get out of our steppers. So they're obviously pushing through metal, wood, plastic, those types of things with a cutter. So they're going to need as much torque as possible. Popular cheap steppers are the Toshiba TB6600 series, and those have their quirks of their own. I have used those, and they do have some bizarre behavior and some problems that you have to watch out for as far as power down sequence, but they can work, and they do produce, if it's a decent one, pretty nice clean waveforms. One of my viewers, Ryan, messaged me with an interesting option. It's a kit from MassMind using a THB6064 chip. I think those are from Sanyo, and that'll be like $30 an axis or $25 an axis, something like that. You can also look at Stepper Online, and they have external stepper bricks with integrated heatsink that are compatible, or I should say built for NEMA 17 and smaller drivers. A lot of these high current guys are for NEMA 23 and larger drivers. Like I said, if it takes a step and direct signal, you should be able to make it work. Other sources for these would be Wantai is a pretty popular budget option. And if you're looking to go whole hog, you can get a Gecko drive. And I'll tell you, I have seen those used in the past. I never owned one, but they are magical. I don't know what they do in there, but the results are glorious, although they will cost you several $100s each. And at that point, you can just kind of bag the open loop stuff and get an integrated driver with optical feedback and make a closed loop system. And this category doesn't necessarily have to include the big expensive options. You can also toss on just the regular old, what are they, the L298N drivers. They're cheap, they're crappy, but they work and they handle a decent amount of current. I have some of those back there. I use them for just spinning general motors like DC motors and things like that. And there's also any number of breakout boards that you can buy or make that you can run off of the SEP and direct signal as well. For instance, if you really wanted a Trinamic TMC 2660, but you can't find it in a StepStack format, you can buy one of their breakout boards. I think it's called the 2660 Bob. They're $20 a piece or something like that. and get that working externally. Don't come to me for troubleshooting because I haven't touched them. Or if you wanted to make your own format of StepStick, that's just fine too. And there's no reason you couldn't plug yet another shield on top of your ramp's shield that had just the stepper sockets, and you could make, I don't know, a larger board for better heat dissipation or something like that. Or go straight up old school and just make a couple of H bridges out of discrete MOSFETs for yourself and run 10 freaking amps through your steppers. I ain't going to tell you how to live your life. Thanks for sticking around through all that. Like I said, we have one more video coming up in the ramp series. It's going to be a summary, wrap-up, post-mortem, post-lude, where do we go from here type of a thing. And that'll lead into the next Sprinter series. And if you came here just for the stepper driver stuff, again, I will be doing more StepStick testing in the close future as soon as I get all those parts in. So subscribe and ring the notification bell. If you like this kind of content and you want to support this channel, I have links in the description, and I also have links to some of the source documents that I used for this video, as well as where you can purchase these, and affiliate links to a couple places that I purchased them, so then at least you know that you're not going to be getting something that's dead on arrival. But that's all for now. So until the next video, get out there and make something awesome.